Hi, this is Andrea Hendricks, and today's topic is the fundamental theorem of algebra. This will finish up the work that we've been doing with polynomial functions. Our objectives for this video are to use the fundamental theorem of algebra to determine the number of zeros of a polynomial function, find all zeros by factoring and using the calculator, and we'll also discuss complex zeros, find a polynomial function that has the given zeros, and then solve a particular application problem. So for our first objective is to use the fundamental theorem of algebra to determine the number of zeros. Well, you may think this is somewhat redundant. We've already talked about that a little bit, but previously our work was centered on just real zeros. We did not get into complex zeros, so this will bring that in. So this theorem states that if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one zero in the complex number system. Well, recall what a complex number system is. That is a system of numbers that have the form a plus bi. And so keep in mind that the real numbers are really part of the complex number system. So whenever we say f has at least one zero in the complex number system, that could be a real zero, or it could be a particular complex number. And remember what I is. I is the square root of -1. So we already know that a polynomial of degree n can have at most n real zeros. We talked about that, meaning how the polynomial crosses the x-axis or touches the x-axis. That tells us how many real zeros we have. But if we use a complex number system, we can say that a polynomial of degree n will have exactly n zeros. Every occurrence of a zero is counted. So that is, if a zero repeats itself, that is two distinct zeros. Linear factorization theorem is something that falls from that, and it says that f of x is a polynomial of degree n where n is greater than 0. F has exactly n linear factors. And we kind of knew that, right? We talked about that if x equals c is a 0, then x minus c is a factor. So if we have exactly n zeros, then we can factor the polynomial as x minus each of those zeros. So that gives us a total of n linear factors. This a sub n is just a coefficient that we may need in the polynomial. So those values of c sub 1, c sub 2, c sub n, those are just complex roots. And again, remember, complex can include real roots. I want to talk just briefly why we say n is greater than 0. Do you recall that something of the form f of x is equal to 5 is a constant function? It really is a polynomial function because it's understood to have x to the 0 power. But a constant function is a horizontal line, so it may not even have, or may not ever cross the x-axis. In fact, it won't unless the value of x, or the value of f of x, is equal to 0. So we have to stipulate that n is greater than 0 for that to be true. So let's look at how many zeros will a polynomial function have. And I've already imported in here the graph from the calculator that you would get. So I just want you thinking about using the graph to know how many real zeros there are, and then would that imply there are some complex zeros as well? We know that f of x equals x squared minus 4x plus 4 has what? Exactly two zeros. Well, look at the calculator graph and see that it touches the x-axis. And remember what happens when it touches. That tells us that we have an even multiplicity, right? In other words, that root is occurring an even number of times. Well, for it to have a power of 2, it has to occur exactly twice. So this is a root of -2, and it occurs twice. So this really has two real zeros, or you can think of it as this. It is 1 0 of multiplicity 2. Now, f of x equals x cubed plus 1, notice that it only crosses the x-axis at one point, so that means it can have only one real zero. That real zero happens to be -1. But our degree is 3, so that means there's 2 other zeros out there somewhere, and those would have to be complex. So some complex numbers. And what about the last one? X to the fourth minus 3x squared minus 4. What touches the x-axis in exactly 2 places? Notice that it is an odd multiplicity. It occurs exactly once there. And so that means that there are 2 real zeros. And we have what? 2 complex zeros. So let's actually go through this process of finding the zeros of the polynomial function by factoring or using the calculator. So this first one, if we wanted to find the zeros of x squared minus 4x plus 4, we can set that equal to 0. This quadratic does factor as x minus 2 times x minus 2. So therefore it has one 0 that repeats itself twice. Right, x equals 2 is a 0. So it has a 0 of 2 with a multiplicity of 2. What about x cubed plus 1? So if we set that equal to 0 and try to factor this, we would get, okay, bring back way back, the sum of cubes, x cubed plus 1 is really x plus 1 times x squared minus x plus 1 is equal to 0. So we know that 1, 0 is our x plus 1 equals 0, which is x equals negative 1. The other zeros come from setting x squared minus x plus 1 equal to 0. Well, this one does not factor at all, at least not over the real numbers, so we have to factor it by using the complex, or rather quadratic formula. So we would have x is equal to the opposite of b, so the opposite of negative 1, plus or minus the square root of b squared, which is negative 1 squared, minus 4 times a, which is 1, times c is 1. And that's all over 2 times a, which is 1. So keep that in mind. The quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So continuing with simplifying this, we would get x is equal to 1 plus or minus the square root of 1 minus 4, which is negative 3, over 2. So this is really 1/2 plus or minus. Remember, the square root of negative 3 is really I on the square root of 3, or we can write that as the square root of 3 over 2 times I. So the zeros are negative 1, and then 1/2 plus the square root of 3 over 2i, and 1/2 minus the square root of 3 over 2i. Now remember, that tells us that we could factor this if we wanted to be x plus 1 times x minus the 1/2 plus the square root of 3 over 2i, and x minus the 1/2 minus the square root of 3 over 2i. Now, if we want to find the zeros of this last function here, we would say x to the fourth minus 3x squared minus 4 is equal to 0. Check to see if this factors. And the factors of 4, whose difference is 3, are 4 and 1, so it does factor. So we would set the factors up as x squared minus 4 and x squared plus 1. So therefore we know that, we know that x squared minus 4 is equal to 0, and x squared plus 1 is equal to 0. So x squared is equal to 4, which gives us plus or minus 2, or x squared is equal to negative 1, which gives us plus or minus the square root of negative 1, which would be plus or minus I. So if we apply that to the factored form, just so you can see that there are n factors, we could write that polynomial as really x plus 2 times x minus 2 times x plus 1 times x minus 1, right? Because that's really x minus negative 2, x minus 2, x minus negative I, and x minus I. So that is the factorization and how it relates to the zeros of the function. Now, these last two are the ones that I had graphs, so just recall that we had one real zero, two complex is what we knew would happen, and then on the last one that we just discussed, we would have had two real zeros and two complex zeros. Now, let me show you another example. F of x is equal to 3x cubed minus 2x squared plus 75x minus 50. So here we would factor. It looks to be factorable by grouping. There are four terms, so let's just see if that works. So if we set 3x cubed minus 2x squared plus 75x minus 50 equal to 0, if we group the first two, there's an x squared in common, and that would leave a, what, 3x minus 2. Between 75x minus 50, there is a, what, 25 in common? So taking a 25 out would leave a 3x minus 2 equals 0. So yes, this is factorable by grouping. We have that 3x minus 2 as a common binomial, and our remaining factor is x squared plus 25. So that tells us that 3x minus 2 is equal to 0. So 3x is equal to 2, or x is equal to 2/3 is one of the zeros. The other zeros are imaginary or complex. We set x squared plus 25 equal to 0 to get x squared is equal to negative 25. So therefore x would be plus or minus the square root of negative 25, which is 5i. So in factored form, we can write this as x minus 2/3 times x minus 5i times x minus a negative 5i, which would really be x plus 5i. And that x minus 2/3, you could also keep it as a 3x minus 2 if you prefer. Okay. Now, I wanted to show you this last one, number 5. F of x is equal to x cubed plus 10x squared plus 33x plus 34, because this is an example of one that is not factorable. Right? I can't factor this by grouping. I can't use the quadratic formula and such, so I'm going to have to use the calculator to find out if there is a real zero that will help us out. So if I pull up the calculator and let's put in x cubed plus 10x squared plus 33x plus 34 and graph it. Okay, this is a third degree, so we know we have 3 zeros, and there's only one real zero, and it appears to be at negative 2. So let's just confirm that. If I look at my table, yeah, negative 2, the y value is 0. So negative 2 is one of the zeros. So that tells us then that x equals negative 2 is a 0, or that x plus 2 is a factor. So what I would need to do now is use long division to find out what the remaining factor is. So if I divide this polynomial by the x plus 2, let's see what that would give us. So x into x cubed is x squared. X squared times x is x cubed plus 2x squared. And remember, then we have to change the signs. So we would have 10x squared minus 2x squared, which is 8x squared, plus 33x. So that would give us what? X into 8x squared plus 33x is plus 8x, right? So 8x times x is 8x squared, plus 8x times 2 is 16x. So now we need to change our signs. So 33x minus 16x is 17x plus 34. And so x goes into 17x 17 times. So 17 times x plus 2 is a 17x plus 34. So that divides evenly, which we knew it would. So that tells us that x cubed plus 10x squared plus 33x plus 34 is really equal to x plus 2 times this quotient of x squared plus 8x plus 17. So to find the other two zeros, now I've got to set this quadratic factor equal to 0. So now we would set x squared plus 8x plus 17 equal to 0 and solve that. Now you could use the quadratic formula. I actually prefer in this one completing the square because there is a 1 on the x squared and an even coefficient of x. So if we use the quadratic formula, completing the square, we would subtract the 17 and then we would complete the square. So half of 8 is 4, squared is 16, but we have to add it to both sides. Now we factor x squared plus 8x plus 16 is really x plus 4 squared, and that's equal to -1. So therefore x plus 4 is equal to plus or minus the square root of -1, which is really I. So our zeros are -4 plus or minus I. So in particular we get -4 plus I and -4 minus I. So that tells us if we wanted to write this whole polynomial in factored form that it would really be x plus 2 times x minus a -4 plus I and times x minus a -4 minus I. And that would be it. So the key lies in factoring. If you have trouble factoring, look at the calculator, see if you can find an exact real zero. Then use that as one of the factors, and then if you need to, long divide to get what the other polynomial factor is, and then you can go from there to solve that. Okay, almost done with this video. Now we want to find a polynomial that has the given zeros. One real important thing to note, as we've seen in those previous examples, is whenever we have complex zeros, they always occur in conjugate pairs. And I mean that if a plus bi is a 0, then a minus bi is a 0. Right? We saw that earlier with the -4 plus I, -4 minus I, and a few others. So you always have two complex zeros, those are pairs occurring together. So if I want to find a polynomial with the given zeros, 3i and -I, that polynomial function f of x would have to be, now there's many answers, you can add different multiplicities and all of this, but we know that if 3 is a 0, then x minus 3 is a factor. If I is a 0, then x minus I is a factor. If -I is a 0, then x minus -I, which is really x plus I, is a factor. Now if you wanted to go further, you could actually multiply this out to get the exact polynomial. X minus I times x plus I, those are the difference of two squares basically, a plus b times a minus b. So if you multiply those out, you would get x squared. The outer is plus I and minus I, which eliminate each other. And -I times I would be a -I squared. But remember, a key thing, that I squared is simply -1. So this is really x squared minus a -1, or x squared plus 1. So we have x minus 3 times x squared plus 1. So if you then wanted to multiply that out further, you would get what? X cubed minus 3x squared plus x minus 3 to be your polynomial. Now, what about 4, 4, and 3 minus I? So this one's a little bit tricky. We have 4 repeating, which means that it comes from a multiplicity of 2. So remember what that tells us, that the factor of x minus 4 is going to have a power of 2 on it. Now, we're only given one complex 0, but we have to recall that those occur in conjugate pairs. So if 3 minus I is a 0, that automatically tells us that 3 plus I is a 0. So our polynomial will have to be of this form. F of x is equal to x minus 4 squared times x minus 3 minus I times x minus 3 plus I. Okay. And if you wanted to multiply that all out, we could certainly do that. I will leave that part for you to do, just not to waste time here, but if you have any questions on how to multiply those out, please contact me. Then on the last one we have 0, negative 2, and 1 plus the square root of 5i. So here again we have one complex 0, which means that there's another one lurking around, which is its conjugate. So we would have the polynomial to be of the form x minus 0, which is just a factor of x minus this negative 2, which is really x plus 2, and then we have x minus our complex roots, which would be x minus 1 plus the square root of 5i, and x minus 1 minus the square root of 5i. And again, you can multiply that all out to figure out what the exact polynomial is. Okay, and let me finish up with one application that I just want you to think about how this polynomial stuff can help you solve these particular types of problems. Here we have a ball is thrown upward from ground level with an initial velocity of 32 feet per second, and its height h is given by h, which is equal to negative 16t squared plus 32t, where t has to be between 0 and 2. You're told that the ball reaches a height of 50 feet. Is this possible? Explain. Well, if we set negative 16t squared plus 32t equal to 50, that would have to mean that negative 16t squared plus 32t minus 50 equals 0 has a real 0 for this to be possible. For that to be possible, that equation there must have a real 0. So we can use our calculator and look at the real zeros of negative 16x squared, or you could solve it by hand if you wanted, plus 32x minus 50, and graph it. Now you can see we don't see anything, but for it to have a real 0 would mean that between 0 and 2 it has to cross the x-axis. And it doesn't. In fact, if we look at the table, notice that we get all of these values that are negative. It's down below the x-axis completely. So in fact, if we just change our window, let's change our y min to be something like negative 200, just so we can see part of the graph. And let's change our scale to be 50. Okay, so the graph is all below the x-axis. For it to be possible, that would have had to cross the x-axis at least one time, and it doesn't. So that would mean that those solutions are complex, which would tell us that this situation is not possible. Okay, so that concludes this video. If you have any questions, please don't hesitate to contact me. Thanks.